Hi, my name is Lisa Walizada, and this is my Project 2 presentation. So, likelihood ratios are used to aid decision making in particular diseases with diagnostic testing, and they are also a common measure for major diseases. Some of the cons for likelihood ratios are that they are difficult to read and they aren't used in every single healthcare scenario. The formula for multimorbidity index is the prevalence of diagnosis among patients who are dead over the prevalence of diagnosis among patients who are alive. And the Charlson Comorbidity Index is used to categorize ICD-9 diagnosis codes within healthcare. So an example of likelihood ratios in SQL include trying to categorize depression. And the way that I did that in this example is that I spot checked for the ICD-9 code I300.4 and labeled that as depression. And the result shows that patient's ID that is matched with depression. You can also see on the right side the total number of patients with and without depression. We selected the sum of depression and categorized that as the column name of A plus C, along with the sum of 1 minus depression as the column name B plus D. And that's how we sort of cleaned our data. And as a result, we finally got the result of patients who are alive among the patients who are dead, and then using that we can calculate our likelihood ratios. So likelihood ratios, the formula for them again is the prevalence of diagnosis among patients with outcomes divided by the prevalence of diagnosis among patients without the outcomes. Using that formula, we're going to be calculating likelihood ratios using the SQL format. We are going to be selecting each of the column names along with the ones with depression and without depression, and then we're going to be using the likelihood ratio formula at the end. And as a result, you should get the ICD-9 codes along with each individual column, and then the likelihood ratios that are calculated at the end. So this is another example of selecting specific ICD-9 codes to find patients who have depression, and these codes can help you specifically find patients who are diagnosed with depression. So the interpretation for likelihood ratios, we use binarization to improve code performance, and it also reduces data processing time. When we're looking at likelihood ratios, any likelihood ratio near 0, the outcome might never happen with the diagnosis. Likelihood ratios near 1 means that there is we know more about the occurrence than before, and likelihood ratios more than 1, the occurrence of outcomes is high. The example for this instance is that patients with ICD-9 code 1I729.92 has a likelihood ratio of 2, which means that the occurrence for that outcome is high in depression. So moving on to ontological adjustment. Ontological adjustment is used to increase sample size and reduce variance in diseases. In doing so, we are going to be using the formula, the syntax stuff to basically create relationships between our concepts to represent associations within the data. And in doing that, you can see a good example of it on the left side. We used the syntax stuff to label each of the ICD-9 codes and then label them with the specific relationship that they have. And as a result, you can see on the left side what the result would look like when we categorized each of the ICD-9 codes. So ontological adjustment is defined as the parameters for rare conditions, and we replace those parameters to create broader concepts. A good example of that is using the format stuff again, and then creating a less than 250 patients to broaden the concept of depression to get less results. So the interpretation for ontology would be that initially we had 17,972 patients affected in the ICD-9 codes for depression, and then after we performed ontological adjustment, we finally got the amount of 8,986 rows affected. So moving on to body system adjustment. Body system adjustment is defined as how patients' diagnosis can combine to predict mortality for multiple morbidities. And you can see this is a great example. We are using the group by function to categorize each of the body system diseases. So, for example, infections, neoplasms, and only worst conditions within the body system matter, and they each independently predict prognosis. So this is another example of body system adjustment. You can see the final results for body system adjustment. Each of the categories is labeled specifically for the ICD-9 body system code and the likelihood ratio associated with the disease. So the body system clarifies how patients' various diagnoses can combine to predict mortality within multiple morbidities. A good example of doing this is we multiplied each of the columns for body system adjustment. We multiplied them together to finally get a final body system adjustment. Within each body system, the worst diagnosis is the only disease that matters. And then across body systems, the worst diagnosis independently predicts prognosis. And multiplying diseases, likelihood ratios are used to find the impact across all disease types. So that's why we multiply all the body system diseases together. And then on the right side, you can see what the result would look like with the patient's IDs and then the score of their likelihood ratios. So the interpretation for body system adjustment is shown below. You can see patient ID 19599 has the worst likelihood ratio of 8.3, which means that this patient would have a high likely of receiving the outcome of occurrence in depression. And in other words, it also means that the patient is 8.3 times more likely to have depression. So moving on to accuracy of predictions, we are going to be using sensitivity and specificity for this topic. Sensitivity is used to indicate the model's ability to correctly detect positive instances or outcomes, and then specificity is used to represent the model's ability to correctly identify negative instances and outcomes. And a good example would be that we identified the column name of score as predicted, and then the column name ID as actual. So calculating sensitivity and specificity, we are going to be dividing true positives with live patients, and then specificity, we are dividing true negatives with dead patients. And when we calculate sensitivity and specificity, you can see on the left side that we use that formula along with the row number to finally calculate the sensitivity and specificity. And as a result, you're going to get a column name for the cutoff, the sensitivity and the specificity results along with their R number. And when we get that result, we're going to be implementing those numbers into a formula that we use to indicate the area under the receiving curve. And on the right side, you can see that I calculated the area under the receiver operating curve, and we finally got an area of 0.04. Now, the result for the area 0.04 is going to be very low, which means that unfortunately we are not able to predict the depression for the data, which means that we would not create a chart for the area under the receiver operating curve. And that is my presentation. Thank you for watching.